The hum. That's what a few technicians at NASA Ames Research Center remember most. A persistent, almost subliminal thrum from the heart of the cosmic weaver. This wasn't just any machine. It was NASA's most advanced quantum computer, a marvel of human ingenuity, tasked with unraveling the universe's deepest secrets. But on a quiet Tuesday last month, May 7, 2025, that hum abruptly ceased. An emergency shutdown protocol was triggered, not for a system failure, not for a power surge. Something far more unsettling had occurred. The official statements were sparse. Technical difficulties, they said, a need for extended diagnostics. But whispers travel faster than light in the scientific community. Something terrible had happened. Those were the hushed words, something that shook the very foundations of their understanding. The cosmic weaver, designed to simulate the cosmos, might have touched something it shouldn't have, or perhaps something had touched it. The implications sent a shiver down the spine of global research. The universe is vast and full of wonders, and perhaps warnings. So, what exactly is a quantum computer? It's not just a speedier version of your desktop. Traditional computers operate using bits, ones and zeros, on or off. Simple, like flipping a light switch. But quantum computers use qubits. Picture a dimmer switch that can be on, off, and everything in between, simultaneously. This is the wonder of superposition. A qubit can hold multiple states at once. This capability to exist in multiple states enables quantum computers to achieve remarkable feats. They can evaluate vast numbers of possibilities simultaneously. Imagine trying to navigate through an enormous maze. A classical computer tests one path at a time, methodical, but slow. A quantum computer? It examines all paths, all at once. This is the strength of quantum parallelism. It has the potential to transform fields we can scarcely imagine. Then there's entanglement. Einstein referred to it as spooky action at a distance. Two qubits can become linked, deeply connected, regardless of the distance between them. Why would NASA, the agency reaching for the stars, require such an extraordinary machine? The universe is incredibly complex. Unimaginably so. Its mysteries are beyond the reach of classical computers. NASA faces challenges that involve processing astronomical volumes of data, or simulating events that span billions of years, or plotting the intricate dance of celestial mechanics for missions to far-off worlds. This is where the Cosmic Weaver was intended to excel. One of its main objectives was to model the elusive characteristics of dark matter and dark energy. These unseen forces constitute most of the universe's mass-energy composition, yet our understanding of them is minimal. The Cosmic Weaver was crafted to execute simulations. Simulations of galactic formation and cosmic structures, aiming to uncover patterns, to discover clues that our current tools overlook. It functioned as a digital telescope, exploring the unseen fabric of reality. Another vital focus was materials science. Envision designing new alloys for spacecraft, alloys that are lighter, stronger, and more resistant to the harshness of space. Quantum computers can simulate molecular interactions with remarkable accuracy. This enables scientists to forecast the properties of new materials before they are ever created. The Cosmic Weaver was engaged in a sophisticated simulation. It was charting potential dark matter filaments across vast intergalactic voids, a task requiring immense computational power. Abruptly, the data stream altered. It wasn't random noise. It wasn't a system failure. The output became organized. Highly structured patterns started to form, patterns that didn't match the expected simulation results. Scientists were puzzled, then alarmed. One team, working late into the night, noticed something truly unsettling. A segment of this unusual output, when decoded from its quantum state, was not random. It was a complex signal, almost like a response. When cross-referenced with archival data from the SETI program, the search for extraterrestrial intelligence, a partial match emerged. A faint, previously unclassified radio signal from the Draco constellation. But the Weaver's signal was no mere echo. It was amplified, coherent. as if it was answering a call. The implications were profound. Was the quantum computer, in its simulation of the universe, somehow tapping into a real, unknown communication? Or, more disturbingly, had its complex quantum state become a beacon, attracting something? The decision was immediate. Unplug it, isolate it. The shutdown of the Cosmic Weaver reverberated far beyond NASA aims. It was a silent acknowledgement that we might have ventured into unknown realms for which we have no maps, no established guidelines. The immediate consequence was, naturally, on NASA's own research. Projects relying on the Weaver's unique capabilities were abruptly paused. Years of planned experiments, now in uncertainty. A significant setback for many ambitious objectives. This wasn't a routine shutdown for maintenance. This was different. This was a quarantine. The sudden stop indicated a potential crisis of control. If a machine designed to explore the cosmos starts showing its own unexplainable behavior, what does that imply? It implies our understanding of these complex systems is incomplete, dangerously so. The scientific community is now buzzing with speculation and a healthy dose of fear. What exactly did NASA encounter? The decision to pull the plug underscores a critical vulnerability. As we create ever more powerful tools, our ability to predict their emergent behaviors diminishes. The Cosmic Weaver was operating at the very edge of known physics, in a realm where intuition fails. Quantum computers herald a new era of discovery. Cures for illnesses, answers to climate challenges, innovative materials that could transform our world. Yet, this tremendous power casts a shadow. The potential for misuse or unintended outcomes is equally immense. This is the quantum paradox. The very traits that make these machines so potent also render them unpredictable in certain ways, and possibly hazardous. Take encryption, for instance. Much of our digital infrastructure is protected by cryptographic algorithms. Algorithms that are currently beyond the reach of classical computers to crack within a feasible time frame. A robust, stable quantum computer could dismantle these defenses instantly. Bank accounts, government secrets, personal information, all exposed. This quantum apocalypse is a widely discussed threat, and the Cosmic Weaver incident, though distinct, serves as a reminder of the disruptive power we are unleashing. Humanity has always sought to push the limits, from crafting the first stone tools to landing on the moon. We are natural-born explorers, yet history is replete with cautionary tales. Tales of ambitions that exceeded wisdom. The myth of Icarus, who flew too close to the sun, melting his wax wings. A stark reminder of the dangers of unchecked ambition. Are we, with quantum computing, crafting a new set of wings? Wings that could elevate us to new heights or lead to a disastrous fall. Early science fiction often depicted superintelligent machines with fear. HAL 9000 in 2001, A Space Odyssey. Skynet in The Terminator. Once considered far-fetched fantasies. But as we develop machines like the Cosmic Weaver, exhibiting unexpected complex behaviors, these fictions seem less fictional. The line between tool and something more begins to blur. The NASA incident is a chilling echo of these stories. The race for quantum supremacy is real. Nations and corporations are pouring in billions, all striving to be the first to unlock its full potential. This competitive pressure can sometimes lead to shortcuts, to a build it now, ask questions later approach. But the questions raised by the Cosmic Weaver shutdown are fundamental. They concern safety. The shutdown of NASA's Cosmic Weaver is a significant setback. A moment to reflect, a clear reminder of the hurdles we face. But this is not the end of our quantum aspirations. Not by a long shot. Every monumental scientific journey encounters obstacles. These are moments that compel us to reassess, to learn, and to innovate. This incident, unsettling as it may be, will ultimately lead to a safer, more resilient quantum technology. It must. The future of quantum computing remains incredibly promising. Its potential to address some of humanity's most critical challenges is undiminished, from developing new medicines to understanding climate change, from exploring the universe to discovering new energy sources. These machines are tools, And like any tool, they can be used for good or for harm. The key lies in our wisdom and foresight, our ability to develop not just the technology, but also the ethical frameworks to guide it. This event will likely spur a renewed focus on quantum safety and ethics. How do we create friendly quantum AIs? How do we maintain control over systems whose intricacies we don't fully understand?